Welcome back to our lecture series on probability theory. I'm Mark Ledbetter, and this is lecture video 11, and we're getting into chapter 2, section 1, discrete random variables. So last time we talked about prior and posterior probabilities. Prior probabilities are the original probabilities, let's say P sub B1, P sub B2. The posterior probabilities would be the conditional probabilities, say P of B1 given R, some other event, P sub B2 given R, etc. So those are the prior and the posterior probabilities. Bayes' theorem is a theorem for going from the probability of, let's say, B given A to the probability of A. So if you want to go from probability of B given A to probability of A given B, then Bayes' theorem is the theorem for you. And we found out that this is equal to the probability of A times the probability of B given A over the probability of B given A, probability of A, plus the probability of B given A prime or A naught given the probability of A prime. And these are complements, of course, the prime. And then we also talked about the law of total probability. And the law of total probability says if B1 to Bm are a partition, then the probability of some other event PA is the sum from 1 to m of P of Bi and A. Okay, so which is equal to the sum from I equals 1 to m of the probability of Bi times the probability of Ba given Bi. So we used our multiplication rule to change that. All right, so this time we're going to talk about section 2.1. We're going to introduce discrete random variables, PMF, CDF, a bar graph, I call it a line graph, and then a probability histogram. So let's get started. We need some definitions. So, but before we do that, let's kind of introduce what we're talking about here. So before we get into discrete probability distributions, we have to make some definitions. So a sample space may be difficult to describe if the elements are not numbers. And so here's an example where we have a rat that's randomly drawn from a cage in a lab, and the sex of the rat is determined. So our sample space here, S, is female and male, and we can abbreviate that as F and M, but they're still not numbers, and we can't perform any real mathematics on this unless we can associate some type of number with our elements of S. So that brings us to the definition of a random variable. And a random variable X, we use capital letters, usually near the end of the alphabet, like X, Y, Z, T, S, etc. A random variable X for some random variable, a random experiment with a space, sample space S. It is a function, and that may surprise you, but it's a function that assigns one, and only one, real number to each element of S. So basically, X of S, little s, that's an element of S, right? So gives us X, where X is some real number, okay? So for our example, we could say that let F equals 0. So how we would write this is we would say if it's a random variable X, so X of F equals 1, and we could say F of or X of M is equal to 0, and now X is a random variable. Okay, so I also want to define the space of X. So it's the set of real numbers X such that X of S equals X, and S is an element of, S are the elements of S. This is also called the support of X. So support is synonymous with space. So you'll see both used, and so that's the way a lot of things are, right? We have more than one word to define something. Sometimes the set of S have elements that are real numbers. And a lot of things do that. If we're measuring heights of adult males, then we're going to measure that with a tape measure, whatever we use, some measuring device, and it's going to give us a number. And so in that case, we can use an identity function for x. And this is what confused me for a while, is that most of the experiments were numbers as an output. So when somebody said it was a function, I was like, what do you mean? And I had to sit down and think about it. So this is what I came up with, is that we're using an identity function when the numbers and when the elements of S are already numbers. Okay, so the space of S is also S. The space of X is also S. So now, let's consider the random experiment where we're rolling a fair die, so 1, and the measurement is the number of dots on the side facing upwards, right? So we have to define what we're measuring there. And so our sample space is the set of numbers from 1 to 6. Now, for each S in capital S, x of little s is equal to s. It's the identity function, and the space of x is s such that x of s is equal to s for all s in s, and that gives us the set of s such that s is in 1 to 6, or simply we could write it as 1 to 6, the set, and that is again s. Your reading assignment is to read from the remark at the bottom of page 41 all the way through about midway through page 42 and stop at the definition 2.1-2. Of course you can read more, but that's what's being assigned. So please read that so you'll understand the homework a little bit better. All right, so discrete random variables. So we've talked about a random variable. Now let's talk about the discrete random variable. So in this case, if the space of x has a countable number of elements, then x is a discrete random variable. And please note that the space of x can either be finite or infinite. So let's do an example where it's finite, and that would be the number of eggs a hen lays in a week. Now I looked this up, and supposedly they can lay 1 egg a day. So it could be that the hen is not laying any eggs, so she doesn't lay any eggs, so 0. It could be that she lays 1 egg every day, and we get 7. So it could be anywhere in between there. Now she can't lay 1.5 eggs in a week, or in a day she can't lay half an egg. So it's discrete. There's a gap between 0 and 1, and 1 and 2, etc. But we can count them. And so the space of x is this set 0 to 7. Now, let's look at an infinite example of an infinite space. A card is randomly selected from a deck of cards with replacement until an ace of clubs is drawn 10 times in a row. So we have to draw the ace of clubs 10 times in a row. So the number of attempts that we're going to have to take is, if this is random, now we said randomly, right? So first we can start with 10. So you have to draw at least 10 times to get 10 in a row, don't you? And then it could be 11, but this could go all the way up, and it could just keep going. You could, if you could live forever, you could get to an infinitely large number of draws required before it happens. So that's an infinite space. Now let's talk about something called a probability mass function, and the PMF is for discrete random variables. Okay? The PMF of a discrete random variable, it's a function that has to satisfy these 3 properties. F of x is going to be positive, okay, when x is in S and the space or support of x. And the sum of all the probability mass function for all x in S in the support or space of X is equal to 1. So the total probability is equal to 1. And then the probability that X is in A for some subset of S is simply equal to the sum of f of x's for the x that are in A. Okay? So think about that. Now, we let f of x equal 0 if x is not in the support of S, and this is the support or space of X. So, confusing notation because S can be the space or it can be the sample space. Okay, space of X or the sample space of the experiment. So the support of a random variable are the values of X such that f of X is greater than 0. So again, this is the same as the space of X. And the support includes the value of X such that the PMF, f of X, is greater than 0. So it's also, again, the space of X. All right. Let's talk about the cumulative distribution function. We use the same thing for discrete. So up here, this is discrete random variables only. Here, this is for both discrete and continuous. It's called the cumulative distribution function. So here, capital F of X, and so little f versus big F, little f, big F, little f, PMF, big F, CDF, big difference. So f of X, capital F of X, is the probability that X is less than or equal to little x. And we usually write this for X between negative infinity and positive infinity, but remember that we do this when X is not in S, f of X equals 0. And so when we take this, the probability when f of X as X approaches infinity is equal to 1. Okay? So the limit is equal to 1. So we'll see that. So for a discrete random variable, f of X can be written not just as the probabilities, but as the sum for I in equals C0 up to f of I, and this is some notation. I'm not sure why we use that, but that's okay, for I equals C0 to X, and oh yeah, so we're letting it be some number, some constant up to X, because we're saying f of X here, and we have to use I. We have to use a different index here to sum across because the max is going to be X, and so that's going to be capital F of X. So we sum up all the possible values up to X in our support or space of X, and that gives us f of X. Now, let's talk about our first discrete distribution, probability distribution. This is the discrete uniform distribution, and we say that a random variable X has a discrete uniform distribution. By the way, there's a continuous uniform distribution too. So, but it's a discrete uniform with parameter n if the PMF, f of X, is equal to, now for the discrete, it's the probability that X is actually exactly little x, or that X is equal to X. So capital X is our random variable, and little x is a value. And I know that the notation at first is confusing. Here we're going to say that X goes from 1 up to m, and it's a integer, positive integer or natural number. So the probability that X, capital X, is equal to little x, some value, is 1 over m. How many values you have. Okay? So it's uniform in that they all have the same probability. And we'll draw this in just a minute and show you what this looks like. And then the CDF, capital F of X, is again the probability that the random variable X is less than or equal to some value X. And for this, because we are defining this discrete uniform as starting at 1, in this case, we defined it as starting at 1. Now we can define it not starting at 1, and then this changes, but this is basically the easiest case. So the lowest value, if it's below, x is below the lowest value it can take on the support of x, or the space of x, then capital F of x, the CDF, the CDF is 0. And then when x is between, let's say, k and k plus 1 in the support of x, then it's k over m. And that's why this is the easiest one, starting at 1. Okay? Makes this an easy formula to write. So it's k over m. And then when m is less than or equal to x, in other words, x is larger than m or equal to m, then the CDF is equal to 1. So all the possible probability of the distribution adds up to 1, and that's a requirement for all probability distributions, that the total probability is 1. Now, we're going to roll a fair die once. We want to find the PMF, the CDF, the probability distribution. I want to find F of 3 and capital F of 3. So here we go. So notice that in this case, m is 6. And if it's a fair die, we can use the classic definition of probability and say, yes, it's 1 over however many we have. We have 6 sides on the die, so little f of x is 1 over 6 if x is 1 in the space, 1 to 6, and OW is otherwise, and so it's 0 otherwise. And so if we add up 1/6 6 times, we get 1, and that's the requirement, right? So now let's look at so here we can write this way, or we can write it this way. This is a more technical way that's more explicit, but this assumes the same thing. We're saying that f of x is equal to 1/6 when x is 1, 2, 3, 4, 5, 6, and it's 0 otherwise. Here, we're being explicit in saying that. Otherwise, it's assumed if we write it this way. Okay, so the CDF, so this has to be written as a step function. You can't, or piecewise function. You can't write it accurately any other way, because if x is below the space of x, the lowest number or the lowest element in the space of x, then the CDF is 0. And then if we are at the kth, between the kth and the kth minus 1. Now notice that this is less than or equal to, so this is the equal to, and this is less than, okay? And the same was true up here. This is less than or equal to. So since we can't have a number, a value between, or we don't have any probability between k and k plus 1, this is simply the probability that x is less than or equal to k, all right? Or less than k plus 1. Those are equivalent. Okay, so think about that. Draw it out and think about it, and you'll see. So f of x here is k over 6 for k either less than or equal, x less than or equal, so x greater than or equal to, k less than or equal to x, or for k plus 1 greater than x. So if x is between k plus 1 but greater than or equal to k, then f of x, the CDF, is k over 6 in this case. And if x is greater than 6 or equal to 6, then the CDF is 1. You can also write this as 0 when x is less than 1. And you can use an interval over here. So a closed interval and an open interval. Closed end, and an open end of the interval. And pretty much the same. So in this case, you notice we're putting x first, so we're talking about it from the viewpoint of x, which makes sense. Now I wanted a probability distribution, so the PMF and the CDF, so I can write it, instead of a formula, I can write it as a table. And let's see, so I wanted the probability distribution, right, not just the formula. I wanted the distribution. So in the discrete case, we can use a table. So x goes up at the top, all the possible values, And then we'll put, this is f of x, little f of x, and of course this is capital F of x. And so you'll see we go 1/6 for all of them. If you add them up, you get 1. So that's what it's supposed to be. And here, since we're doing the cumulative, so we add up all the values of f of x up to this point. So far we only have 1, so we've 1/6. Then we add 1/6 to that to get 2/6. And then we add 1/6 of that to get 3/6. And then we add 1/6 to get 4/6. I think you can see the point. When we add the last one, we better get 1. And we don't sum these up. That makes no sense. So then we ask for f of 3. So once we have the table like this, it's very easy to answer the next problem. We just look up here at 3, and there it is, 1/6. And for f of 3, this the CDF, the same thing. Here's 3, so here's the CDF of 3. And 3/6. So I would leave it again as 3/6 unless you're asked to simplify it, which I'm probably not going to. You may make things, future calculations, more difficult for yourself if you change it to a half. So, by the definition of the CDF, f of 3.5 is the same as f of 3, which is 1/2. I'm going to use 1/2 this time. Why? So think about that. Here we have, because for f of x between for x between 3 and 4, not equal to either one, f of x is 0. So we add absolutely nothing to it when we move up a half, because there's no probability there. And we can see that with this line graph. They call it a bar graph, but it's really a line graph, where we've plotted for each of the x's, we've plotted the values, and we've plotted the probability at each of these values, which is 1/6. But there is no, so at 3.5, the height of f of x is 0. It only has height at these points, 0, at 1, 2, 3, 4, 5, or 6. Okay. Now, here is the CDF, right? And so this is a step function. It is right continuous. So it's right continuous. And you'll see that as we go to a point from the right, it's continuous. From the left, it's not. That's open point, so it's not continuous at that point from the left. It is continuous at that value of x from the right. Okay, it's a right continuous function. And this is a probability histogram for the die, for rolling the die. So the possible values are 1, 2, 3, 4, 5, and 6. It's the same probability for all of them, 1/6. And what we do is we go halfway in between. So here's 1, here's 2. We go to 1.5, and that's where we draw the line, halfway in between. And we act like it's constant across here for a histogram. You'll find out the reason for this when we start doing approximations for the say the normal or some other continuous distribution. All right, so this has been a long video. I'm sorry, but I had to get this done, and I wanted to give you some extra information, not just go over this too quickly. So please don't forget, scan and upload your lecture notes before midnight on the date listed in the course calendar. They're your lecture notes, so make them neat so you can read them. They do some good for you. I would start a formula sheet, if you haven't already, to use for tests and for the homework. And I also would say that in grad school and in undergrad too, in this type of course, it really helped me to have a list of definitions, theorems, corollaries, and remarks all on the same sheets of paper together, so that when I go to do a problem, especially a proof, I had them all right there to quickly refer to. If you have questions, please come to virtual office hours. If those just don't work for you, by all means, email me. I'm happy to help you, and we'll see you next time.